Hello everyone, I hope all of you are doing good, and today I am back with a video series on Class 9 Maths number systems. Numbers. Do you think that they play a critical role in mathematics? Of course, we can't think of mathematics without numbers. Whenever we want to quantify an object, we need numbers. If I ask you, how many biscuits do you have? How would you reply? You may say, I have many biscuits. But the word many might mean you have 2 biscuits, you have 20 biscuits, or you have 20,000 biscuits. So how do I know? So that is why in order to exactly define how many, you need numbers. And all these, whether 2, 20, 20,000, 20 lakhs, they are all numbers. Now when we talk about number systems, we are going to talk about many different types of numbers. Let's start with the basic ones. Let's say I have 10 fingers, 2 ears, 2 eyes, 1 nose. So all these basic numbers like 1, 2, 3, 4, 5 and so on, they are natural numbers. But they aren't enough. What about a situation where I want to say that I have no biscuits at all? So do we have a number to define none? Of course, and that number is 0. So the moment we include 0 along with the remaining natural numbers, we get whole numbers, right? But again, whole numbers are also not enough, and that is why we have the third type of number, that is integers. And what are they? Let's see. Sometimes we come across situations where we need numbers which are even lesser than 0. Let's say we want to measure the temperature of an ice cube and the temperature is lesser than 0 degree, and that is where we talk about the negative numbers. Just the way we have +1, +2, +3, +4 after 0, similarly we have -1, -2, -3, -4 and so on below 0. So all these negative numbers and positive numbers along with the 0 form the integers. Then we have the fourth type of number, which is rational numbers. What are they? Let's think of this situation. Suppose your mom tells you that, okay, we have pizza for dinner tonight. So how many pizza will you eat? 1, 2 or 3? So you'll be thinking, how can I eat one entire pizza? Forget about eating 2 or 3. So your mom would say, fine, then you eat 0 pizza. But then you do not want to miss the pizza. You want to eat some, but then how much? So you may say that, okay, I want to eat half of the pizza or 1/4 of the pizza. So what you mean is, I want to eat 1 slice out of the 4 slices or 1 slice out of the 2 slices. So what is this 1/2 or 1/4? They are ratios, and these type of numbers form the rational numbers. Finally, the fifth type, which is little more complicated, and these numbers are not rational numbers. For example, √2, √3 or pi. These are all called irrational numbers. So in this video, our agenda would be to talk about all of these different types of numbers. In fact, right away we are going to talk about these 5 types of numbers and see them in more detail on a number line. All these 5 types of numbers that we discussed so far, they are together termed as real numbers. So basically in this lesson, we are going to deal with real numbers. If you look at this picture, this very clearly tells you what includes what. Let's start with natural numbers. As I said, natural number starts from 1, 1, 2, 3, so on till infinity, right? Now, if we look at the number line, where are the natural numbers? So all the numbers starting from 1 till infinity. So these are all natural numbers, and the natural numbers are denoted by a capital N. Cool? So that's natural number. Next one is a whole number. What is whole number? All the natural numbers plus 0. So the extra thing that is there in whole number is a 0. 0 and all the natural numbers, that's whole number. So if you look at this picture, you see that natural number is inside the whole number. That means all natural numbers are also whole numbers, but all whole numbers are not natural numbers. So if you look at the number line, so the whole numbers would start from 0. So all the numbers starting from 0 till infinity. So that's whole number. Third one is integers. So integers, all the natural numbers, all the whole numbers, and also the negative numbers. So basically in integers, we have all the negative numbers like -1, -2, -3 and so on, plus 0, plus all the positive numbers. So that's integer. So where are they on the number line? All these numbers that you see here, whether the negative number or the 0 or the positive numbers, they are all integers. The fourth one is rational numbers. Okay, meanwhile, I forgot to tell you how do we denote them. So whole numbers denoted by a capital W, integers denoted by a capital Z. Surprised? Why not I and why Z? Well, so this Z is derived from a German word called zählen, which means to count. So the numbers are all about counting, right? So from there it got this letter Z, and therefore integers are denoted by Z. Let's move on to the next one, that is rational numbers. And what are rational numbers? The ratios. 1 by 2, 2 by 3, 3 by 4, they are all rational numbers, right? So all of these numbers, whether it is 2 can be written as a rational number, because rational number has to be in the form of P by Q such that Q is not equal to 0. So that's how we define a rational number. So any of these numbers that we have discussed so far can be written as a rational number. For example, if I talk about 3, so 3 can be written as 3 by 1, which is in the form of P by Q, Q not equal to 0. If I talk about -3 can be written as a rational number, -3 by 1. If I talk about 0 can be written as rational number, that is 0 by 1, right? So all of these numbers, natural number, whole number, integers, they are all rational numbers. And where do we find them on the number line? So rational numbers, so these integers that we see, they are all rational numbers, but in between any two of these integers, there exists many rational numbers. Moving on to the fifth type, that okay, how do we denote rational number? By a capital Q. Why Q? So rational, the word rational is derived from ratio, right? And Q is derived from the word quotient, right? Because when we talk about ratio, we're basically trying to divide two numbers, and that is where we get a quotient. So that's why Q. Irrational numbers, all those numbers which cannot be represented in the form of P by Q. And where do we see them on the number line? Because irrational numbers are numbers like √2, √3, √5, pi. So we really do not see them directly on the number line, but yes, they do exist on the number line, and we will learn how do we point out an irrational number on the number line. So we will learn about that a little later. Please remember that there are infinite number of rational numbers between any two rational number. Surprising? Yes, but that's true. You just think in your mind about any two numbers. Let's say if you talk about say 1 and 2, you will have plenty of rational numbers between them. For example, 3 by 2 would lie, which is actually 1.5, would lie somewhere between 1 and 2. And you have so many numbers like that lying between 1 and 2. Are you curious to know that how do we find out numbers lying between two rational numbers? Let's understand that. Let's try to find out 5 rational numbers between 1 and 2. Okay, so we have to find between these two numbers, that is 1 and 2. So 1 can be written as 1 by 1, 2 can be written as 2 by 1, correct? Now, how do we find out these numbers? Now, just now I told you that there exists infinite number of rational numbers between any two numbers. So with that logic, there exists infinite number of rational numbers between 1 and 2. So I will show you how, okay? So let's do one thing. Let us multiply both the numerator and the denominator by 10. right? So overall value remains the same, because if I multiply the denominator as well as the numerator by 10, so overall value is going to be the same. So what is this that we get? We get 10 by 10 and we get 20 by 10. Okay, so now let us suppose if I have to find out values between 10 by 10 and 20 by 10. What will be those values? They could be 11 by 10, 12 by 10, 13 by 10, 14 by 10, 15 by 10, so on, 19 by 10 and then 20 by 10. So all these numbers will lie between 10 by 10 and 20 by 10. So I can say that all these rational numbers exist between 1 and 2, because they exist between 10 by 10, which is 1, and 20 by 10, that which is 2. So basically all these numbers exist between 1 and 2. Now let us suppose I do the same thing, but instead of 10, I multiply this by 100. So what do we get? 100 by 100, and this side we get 200 by 100. Correct? Now, if I ask you to write down numbers that come between 100 by 100 and 200 by 100. So, what will be those numbers? 101 by 100, 102 by 100, 103 by 100, and so on till 199 by 100. Correct? So, what I'm trying to tell is, the moment we convert these rational number into another equivalent rational number by multiplying the numerator and the denominator by a same number, we will be able to identify many rational numbers in between. That is why we say that between any two numbers there exist infinite number of rational numbers. So, the question is just asking for 5 rational numbers, which is nothing. Any 5 of these rational numbers exist between 1 and 2. Find 5 rational numbers between 3 by 5 and 4 by 5. Do I need to do it, or you'll try it on your own? I think you'll be able to try it on your own. I'll just give a slight hint. So here you have 3 by 5 and 4 by 5. So in first option you can multiply both the numerator and denominator by 10. So it becomes 30 by 50. This becomes 40 by 50. Therefore the numbers in between are 31 by 50, 32 by 50, 33 by 50, so on till 39 by 50. You can also multiply it by 100. So it becomes 300 by 500, and this becomes 400 by 500. So overall it becomes 301 by 500, 302 by 500. So these are the numbers in between. Now you may ask, why is it necessary to multiply by 10? It is not at all necessary. If you want, you can multiply the numerator and denominator by 9. That's also fine. But then in that case, you will actually, your calculations will become difficult. Here it's like you're multiplying by 10. So 10 into 3 is 30. 10 into 5 is 50. But the moment you multiply it by 9 or 17, what happens is your calculation becomes more difficult. So since we already know that in between these two numbers there exist infinite numbers, and we anyways just need to find any 5 numbers. So let's go by the easiest route. So in this fashion, I think you will be able to identify 5 rational numbers. So based on our understanding of the different types of numbers, let's try a few true or false. Every integer is a rational number. Now, if you understand this clearly and if you have this picture in your mind, this will help you to answer all of these kind of logical questions. Where are integers? The green one is integer. Every integer is a rational number. Yes, because you can see all integers are contained within the rational number. So this is true. Every rational number is an integer. Is that true? No, because rational numbers, all rational numbers are not integer. There are many rational numbers which are not integers. Correct? For example, you talk about any integer, -3, -5, -27, they are all rational numbers. But you talk about any rational number, for example, if I talk about, say, -2 by 3, that is not an integer. So this is false. Every natural number is a whole number. That is true, because you can see that all the natural number are contained within the whole number. So this is true. Every rational number is a whole number. That is absolutely false, because you can see that whole number is contained inside rational number. That means all whole numbers are rational numbers, but all rational numbers are not whole numbers. every real number is an irrational number. That's not possible because all of these numbers are real numbers. So a real number can either be an irrational number or a rational number, right? So this is false. So every point on number line is root m, where m is a natural number. So is that correct? Okay, so with that, even if I assume that this is correct, that actually means that on the number line, we will only have numbers like root 1, root 2, root 3, root 4 and so on. Right? But is that true? No, because on the number line, we also have the whole number, the negative numbers, in fact, the integers, we have the rational numbers, we also have the irrational numbers. So basically, we have all the real numbers on the number line. So it will be incorrect to say that we only have numbers which is in the form of root m, where m is a natural number. So this is absolutely false. We all know by now how a number line looks. So the number line displays all the integers, the positive numbers, the negative numbers and the zero, as is seen on the screen, right? Now, representing a natural number or a whole number or an integer is pretty simple because we can straight away see them on the number line. What is trickier is to represent an irrational number. Let us suppose we have to locate root over 2 on a number line. So root over 2 is an irrational number, and when we look at the number line, we do not see it anywhere on the number line. So what is the process that we will apply to locate the exact position of root over 2? So here we will take help of the Pythagoras theorem. So if you remember the Pythagoras theorem, it states that in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendicular and the base. So that's Pythagoras theorem. Okay. Now here what we will do is our step 1 would be, how can I write root over 2? So how can I, if I assume that root over 2 is my hypotenuse, then we have to write it in the form of root over p square plus b square. So here we can write root over 2 as root over 1 square plus 1 square. That means if at all I can construct a right angle triangle such that perpendicular and base are equal to 1 units each, then the hypotenuse will be root over 2 units. So this is the main logic that we are going to use here. Okay, so now let's try to locate root over 2. So we will use this logic that I told you just now. So where is 1 unit? So from 0 to 1. So we will need a ruler, a protractor and a compass along with obviously a pencil. So this is 0, this is 1. So 0 to 1 is 1 unit. So let us make this our base of this triangle, right? So base हमारा बन गया. Now what we will do is from 1, let us try to find out the distance of 1 unit. So whatever this distance is, so you measure that with the compass and then again measure the same distance here, drawing a perpendicular. So you can draw a perpendicular using the protractor. So in this fashion you draw this. So basically this is 1 unit and till this point this is also 1 unit. So all that we need to do now is we need to join these 2 points. So what happens? This becomes root over 2 because we have actually drawn a right angle triangle with perpendicular and base equal to 1 unit. Now you place the compass here at O and measure this distance. So how much distance is this? So using that you draw an arc like this. So wherever this arc crosses the number line, that point is the position of root over 2. So I hope you got the logic. So here the main logic is this Pythagoras theorem concept. Now I think it will be clearer when we look at the next example. So here we will try to locate root over 3 on number line. As I had discussed earlier, our main agenda will be how can we write root 3 in terms of Pythagoras theorem, as in root over 3 is equal to root over what? So I can write it as root over 2 plus 1. So this can be written as root over root 2 whole square plus 1 square. So basically now we need to draw a right angle triangle such that maybe one of the base and perpendicular, they are 1 and root over 2 respectively, and then the hypotenuse becomes root over 3. So this is our desired construction. And how do we do it? So for this, we first need to draw a root over 2. So that we already learned in our previous example. So again, using the same things, we will draw the same. So first we will draw root over 2. So for that, this is our 1 unit. So again, from point 1, we will draw a perpendicular and we will cut it at 1 unit such that this is also 1 unit. Now when we join these 2 points, then this becomes root over 2. So now what we need to do next? So we have already drawn root over 2 here. Now we need to draw this one. So we need to draw a perpendicular. So that is what we do. So we have drawn a perpendicular here, and then we will measure 1 unit using a compass, and then you can cut it at that point. So let's say if this much distance is 1 unit. Now when you join these 2 points, then what is this distance? This distance is root over 3. Now using the compass, you can measure this distance and then make a cut somewhere here. And that's how you find out the position of root over 3 on the number line. So in a similar way, you can try out yourself on how to locate root over 5. So that could be an exercise for you. Let us now see how do we represent any general number root over x in a number line geometrically. Now with this, we will be able to represent any number which is in the form of root x. It could be numbers like root over 2.3, it could be root over 7.5, it could be root over 8, it could be anything, right? So how do we represent such numbers in number line geometrically? So here we will follow few steps. So the first step would be, first draw a line of length x. Let's call that AB. So that is step number 1. Step number 2. So you already have AB now. Now what you have to do is extend it by 1 unit and name this point as C. So now you have AB is equal to x and BC is equal to 1. Okay. Now in step number 3, identify the midpoint of this line AC. So now you have the entire line segment is AC, right? So you have to identify the midpoint. So let us suppose that this is the midpoint. Mark it as O. Considering this as the center, this O as the center and OC as the radius, draw a semicircle like this, right? So till here it is clear, right? So where OC is the radius of this semicircle. Now join this point. So from B, draw a perpendicular and join it to the semicircle. So this height becomes root over x. So this is how you get root over x. So once you get root over x, then it is pretty simple, right? With root x, you can measure the distance using a compass and then you can locate it on the number line. Now, you may ask that, okay, let us suppose I blindly follow the steps that you told just now. But how do we know that doing such complicated things will actually give me the value of root x? Like as in, how do we know that this line is actually root over x? So we can prove that geometrically. How? Let us see. Now just focus on this. Now let us call this point as D. Okay. Now let us suppose if I join point O with point D. So what do we get? We get a right angle triangle. OBD is a right angle. So triangle BOD. This is a right angled triangle. So therefore, if we apply Pythagoras theorem to this triangle, then we can say that BD square is equal to OD square minus OB square, right? And what is OD? So OD is nothing but the radius of this semicircle. So what is the value of this radius? Now we know that this entire thing is x. This is 1. So this entire length is x plus 1 and half of x plus 1 would be x plus 1 by 2. So radius is equal to x plus 1 by 2. So OD will be equal to x plus 1 by 2 whole square minus OB square. What is OB? This distance. How do we find this distance? So this distance will basically be OC, which is again the radius, minus 1, that is BC. So that means x plus 1 by 2 minus 1, that is OB. So if we calculate it, this is x plus 1 by 2 whole square minus x minus 1 by 2 whole square. Now let us solve this. So here it will be 4 x plus 1 whole square, a square plus b square plus 2ab minus a square plus b square minus 2ab. So if we further calculate, we see x square will cancel, 1 will cancel. So we get 4x by 4, that is equal to x. So we see BD is equal to root over x. So that actually proves that this length BD will be equal to root over x. So this is how we represent root over x in a number line geometrically. Now it's time that we try it out with few numbers. So let us suppose if we have to represent root over 9.3 on the number line. So what we will do? Step 1. We will first draw a line of length 9.3. Now let us say we name it as AB. Then we will extend it by 1 unit up to point C. Okay. Now we identify the midpoint, which is O. Once we identify the midpoint, then what we do? We draw a semicircle like this. Great. Then what we do? We have to join point B to this semicircle, drawing a perpendicular. So basically this length becomes root over 9.3. Now when I talk about real numbers, we majorly talk about the rational numbers and the irrational numbers. Okay. Now the rational numbers, as we all know, are in the form of P by Q, where Q is not equal to 0. Now how are we going to convert it into decimal form? By the division method, the normal long division method. Now we will always come across two situations. One situation could be that the remainder is 0. And in such cases, the decimal that we get is going to be a terminating decimal or a non-repeating decimal. The second situation could be that the remainder is never 0 and we see that a set of numbers keep repeating over and again. So in such cases, the decimals would be a repeating decimal or a non-terminating decimal. Whereas when I talk about an irrational number, the remainder is never 0 and there is no repetition. Therefore, we get a non-repeating, non-terminating decimal. Too much of information, right? So all confused. What is repeating? What is not repeating? So let us understand the same thing using examples. So let us take examples for each of these categories. So in the first category, let us consider this example of 7 by 8. Let us consider this rational number. Now if I convert it into decimal, what happens? So 7 by 8. So if I have to convert into decimal, so this is how it will be. So 8 is a 64. So we are left with 6. So 8 7s are 56. This is 4. 8 5s are 40. So what happens? What is the remainder that we get here? Remainder is 0. And what is the type of decimal that we get here? It is non-repeating. So the numbers or the digits are not repeating. So it is non-repeating and the remainder is 0. So this is what I meant. So if we have a rational number, so for a rational number, one possibility could be that the remainder is 0. And if the remainder is 0, in that case, the decimal expression will be non-repeating. So you will just have terminating decimal. This is what we call as terminating decimal. That means it ends, it terminates. Okay. Now let us look at the second possibility for a rational number only. So in this case, we will say that the remainder is not 0. For example, let us take the example of 10 by 3. Let us try to convert it into decimal. So 10 by 3, so 3 3s are 9. 1. So we take a decimal here. So 3 3s are 9 again. 1 again. 3 3s are 9. 1 again. 3 3s are 9. 1 again, and so on. So you see the remainder is not 0 in this case. And what is happening to the decimal expression? It will continue like this, 3.3333333 till infinity. right? So how do we express this? We write it like this, that 10 by 3 can be written as 3.3 bar. So this dash on top shows that this particular digit 3 will continue to repeat. So what is happening? So this is a repeating decimal or non-terminating decimal, because here the decimal is not ending, it is continuing. This digit will keep coming over and again. So that could be a case. Now, it is not necessary that the same digit will keep repeating all the time. There could be another scenario where the remainder is not 0 and where the digits are repeating, but it is not just one digit which is repeating, but a string of digits which are repeating. For example, let us take 1 by 7. Okay, let's try to convert it into the decimal format. So what happens? 7 ones is 7, so we have 3. 7 fours are 28. 7 twos are 14. 7 eights are 56. 7 fives are 35. 7 sevens are 49. Now again 7 1 is a 7, so we have 3. 7 4 is a 28. So this is going to be a very long division, but what you will notice is in this pattern the remainder will not be 0 and this will repeating, but you see it is not just one single digit which is repeating, but the series of digit which is repeating. This entire series 1 4 2 8 5 7 will repeat. You see 1 4 already started coming up, and now you will gradually see 2 8 5 7. So it will be something like this: 0.142857, 1428571, 1428557, and so on. Clear? But both of these categories, they fall under the category of rational number. So in rational number, basically we have these two possibilities. One possibility, remainder is 0. So it is a terminating decimal or non-repeating decimal. Second possibility is remainder is not 0. In that case, it is a repeating decimal or a non-terminating decimal. So in that case, again, you could have two options. One option could be one digit keeps repeating. The other option could be that a string of digits, they keep repeating. Clear? So far, so good. Great. Now let's look at the irrational numbers. So in case of irrational numbers, we are talking about such numbers where the remainder is not 0 and also the decimals are non-repeating. For example, if I have to take examples of irrational numbers, let's see if I talk about pi. What is the value of pi? We take it as approximation as 3.14, but it is not 3.14. The actual value is 3.1415926535897, and it continues. And you do not see any kind of repetition anywhere. So it is a non-repeating decimal, and also obviously since it is not ending, so it is non-terminating also, so the remainder is not 0. So non-repeating, non-terminating decimals, that means it is an irrational number. Similarly, you take any irrational number, for example, root over 2. Again, we take the value as approximately as 1.414, but actually it is 1.41421356237 and so on. And again, it continues, and there is no pattern, there is no repetition. So why I told this? So now looking at the decimals only, you can tell whether the number would be a rational number or an irrational number. So if you see that it is a non-terminating, non-repeating decimal, that means it is irrational number. If it is a terminating decimal, then it is definitely rational number. If it is a non-terminating decimal, but it is a repeating decimal, in that case we will say it is a rational number. So based on this knowledge, you can easily look at a decimal number and tell whether it is rational or irrational. So it's time to look at some questions. So that's practice time. Show that 0.333333 is a rational number. Express it in the form of p by q, where p and q are integers and q not equal to 0. So first of all, just looking at the decimal format, what can we say? It is 0.3 bar because 3 is repeating. So it is a repeating decimal. So this is a rational number, because for irrational number this has to be non-repeating, non-terminating, right? But that's not the case. So this is a rational number. So we quickly answered. Now we also need to write it in the form of P by Q. So how will we write it in the form of P by Q? So for that we follow a very simple trick. First tell me how many digits are repeating in this case. Only one digit, that's 3. Since one digit is repeating, what we will do is, we will first say that okay, x is equal to 0.3333, so on. Now we will multiply this entire thing by 10. Why by 10? So I'll tell you why. So you will get to know that a few seconds later. But for now you just know that whenever you have one digit repeating, you multiply it by 10. You have 2 digits repeating, multiply it by 100. 3 digits repeating, multiply it by 1000. So that's how you have to do it. So if I multiply this entire equation by 10, it becomes 10x is equal to, so this becomes 3.3333. It continues to repeat like this, right? Now let us suppose if I subtract these two equations, as in if I subtract equation 1 from 2, so what do we get? So we get 9x, so 10x minus x will be 9x, and 3.333333 minus 0.333333 will be equal to 3, because 0.33 is like it's till infinity for both of these. So this will become 3. So x will be equal to 3 by 9, which is equal to 1 by 3. And what is x? X is basically 0.3 bar. So in terms of P by Q, we have already written it. It was simple, isn't it? So now if I ask you, why did I multiply it by 10? Can you answer? Of course, because the moment I multiplied it by 10, what happened? Decimal के बाद वाला part गायब हो गया. So we got rid of this repeating part, because that was creating all the trouble for us, right? Because we don't know how many times 3 is repeating. So how do we handle that? So we managed to get rid of that part, but still managed to find out the P by Q form of x. So this is the trick that we are going to follow. So let's look at one more question. Is 12.234435623459, I think it will take too much time to read the entire thing. Is this an irrational number? So what do you think? Do we see repetition? No. But do we see that it is terminating? No. So basically this is an example of a non-repeating, also non-terminating decimal. Therefore, this is an irrational number. So yes, this is an irrational number. Moving ahead to the next question. Find irrational numbers between 1 by 7 and 2 by 7. Even before I try to find that, first of all, I will convert these two numbers into their decimal expressions. And how will we do that? Simple, by division method. So 1 by 7 can be written as 0.142857 bar, because this entire string of digits keep repeating, right? And what is 2 by 7? Okay, another interesting thing. Now you do not need to divide this entire 2 by 7 thing. So if 1 by 7 is this, so 2 by 7 will be 2 times of this. So you can simply multiply this by 2. So you will get 0.285714 bar, right? So now we have these two numbers in their decimal form. Now we have to find out numbers between these two numbers. Now there will be infinite irrational numbers between these two numbers. So what we need to do? We need to find any number that is non-repeating, non-terminating between these two numbers. So you can randomly pick any number. So let us suppose if I randomly pick a number like this, say between 0.14 and 0.28, it has to lie in between these two numbers. So you can say 0.16238124591364. What is this? This is non-terminating, this is non-repeating. So this is an irrational number, and you can literally pick any number between these two, just that it should lie between 0.142 and 0.28. So it could be 0.2513694235. It could be anything. So the entire logic is that it has to lie between these two numbers, and it has to be non-repeating and non-terminating. So moving ahead with the next question, write the following in decimal form. 36 by 100. So 36 by 100 can be written as 0.36, and this is a terminating decimal. 1 by 11. So if we actually convert it into the decimal form, what do we get? We get 0.09 bar, because it keeps repeating. So this is non-terminating and repeating. 41 1 by 8. So this can be written as 4.125, because 4 1 by 8. So this is not 41 by 8. This is basically 4 1 by 8. So this will be 8 4s are 32 plus 1 33 by 8. So this will be written as 4.125, and that is a terminating decimal. Then we have 2 by 11. 2 by 11 can be written as 0.18. So this is also non-terminating, repeating. So in this fashion, we can write down the rational numbers in their decimal form. You know that 1 by 7 is equal to 0.142857, where this entire thing keeps repeating. Predict the decimal expansion of 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7 without doing long division. That's pretty simple. So if we know 1 by 7, how do we find 2 by 7? By multiplying it by 2. Simple. So in a similar way, if we have to write its corresponding decimal expression, we will simply multiply it by 2. So 2 by 7 will be equal to 2 multiplied by 0.142857 bar. So this becomes equal to 0.285714 bar. So in a similar way, you can find out 3 by 7, 4 by 7 and so on. And for your verification purpose, you can actually do, just to verify, I'm showing you, you can actually perform the division method to see that if this is what you get. And you will get the same thing. So let's say 0.072 are 14, so 6, 7 8 are 56, 4, 7 5 are 35, 5, 7 7s are 49, 1. So you see, you are actually getting the same thing, right? So whenever you are given 1 by 7, you have to find out 2 by 3 by 4 by 5 by 7. Just multiply by 2, 3, 4, 5 or whatever number you want to. Express in form of P by Q, where P and Q are integers and Q not equal to 0. So sometime back we discussed about the trick that we are going to follow whenever we have to write a decimal, that to a repeating decimal in the form of P by Q. So let us try with all these three. So let us first try with the first one. Let us suppose X is given as 0.6666 and it keeps repeating. So how many digits are repeating here? 1. So we will multiply it by 10. So this becomes 6.6666 and so on. Now we subtract the first equation from the second equation. As a result, we get 9x is equal to 6. Therefore, x is equal to 6 by 9, which is equal to 2 by 3. And that's our answer. It's in the form of P by Q. Great. Now let us look at the second one, which is 0.47. So here we have 2 decimals after the decimal point, right? So let us first multiply. So this is x. So let us multiply it by 10x. So what do we get? 0. So we get 4.7777 and it keeps repeating. If we multiply it by 100x, what will we get? We will get 47.7777 and so on. Now, why did we multiply it by 100x as well? Because if we multiply it by 10x, now even if we subtract these two, it will not solve the purpose. So we want to subtract two such equations such that after point we just have the repeating number. But in this case, that's not happening because here it is 0.777. But in the first case, it is 0.4777. So we want to get rid of that 4 as well. Correct? So we found 10x, then we found 100x. Now if you see, if we subtract 10x and 100x, then we can get rid of this entire repeating part. So let us do that. Let us subtract 10x from 100x. So we get 90x is equal to 43. So x is equal to 43 by 90. So that's our answer, and that's in the form of p by q, where p and q are integer and q not equal to 0. In the third option C, we have 0.001. So here how many repeating digits do we have? 3. So we will multiply it by 1000. So this will be 1000. So x is equal to this. So 1000x will be equal to 1.001001 and so on. So now if we subtract these two, so what do we get? We get 999x is equal to 1. Or x is equal to 1 by 999, and that's in the form of p by q. So now the trick is pretty simple. So our whole idea is when we subtract the two equations, we should get rid of the entire repeating part. So that's the idea. Classify rational or irrational number. So looking at these numbers, we have to tell which is a rational number and which is an irrational number. So first one, root over 23. So this is not a perfect square. Any square root which is not a perfect square is always an irrational number. Second option, root over 225. So this is a perfect square because root over 225 is equal to 15. Therefore, this is a perfect square and therefore this is a rational number. 0.3796. So this is a terminating decimal. Therefore, this is a rational number. 7.478478 and so on. So this is non-terminating, but this is repeating because we can see that 478 keeps repeating. So therefore this is also rational number. 1.1011001100001100001. So here we see this is also non-terminating and this is also non-repeating because none of the digit or string of digits keep repeating. The exact string of digit has to repeat. So if it has to be repeating, it has to be like this, 101, 101, 101, 101, like that. So this is non-terminating, non-repeating. Therefore this is irrational. Operations, of course, the mathematical operations like addition, subtraction, multiplication and division. So what we notice is both rational and irrational numbers, they follow the commutative property, associative property and distributive property for addition and multiplication. A lot of you must be thinking, what are these properties? You must have studied about them in your junior classes, but still we are going to do a very quick recap. Commutative property for multiplication tells us that A multiplied by B is equal to B multiplied by A. In case of addition, it tells us that A plus B is equal to B plus A. Next is associative property. It states that if there are three real numbers A, B, C, then A multiplied by B multiplied by C is equal to A multiplied by B then multiplied by C. Similarly, in case of addition, it tells that A plus B plus C is equal to A plus B plus C. Then comes the distributive property, which tells that A multiplied by B plus C is equal to A multiplied by B plus A multiplied by C. So if you see, all these properties are something which we have been learning since junior classes. So all that we are trying to tell is these properties are also followed by real numbers, that is both rational and irrational numbers. Now, please note an important thing here. If we add, subtract, multiply or divide two rational numbers, we get a rational number. But that is not true for irrational number. It is not necessary that if we multiply two irrational number, we will always get an irrational number. For example, root over 2 is an irrational number. But if it is multiplied by root over 2, we get 2, which is a rational number. So the product of two irrational numbers becomes rational in this case. So let us take a look at what are the different operations that we can do between a rational and an irrational number and what will be the output that we will get. So this table will help us to identify it in a better way. So we will do 4 operations, that is addition, subtraction, multiplication and division. First we'll try with rational and rational, then we'll try with irrational and irrational, then we will try with rational and irrational. Okay, so we will take examples and see what happens. Okay, so let's start with rational and rational addition. So let's try with some examples. Let us suppose 2 plus 2, two rational numbers. When you add them, what do you get? You get 4, which is again a rational number. If we talk about subtraction, let us suppose 2 minus 1, you get 1, which is a rational number. Talk about multiplication, 2 into 4, you get 8, which is a rational number. Divide, 2 divided by 5, which is a rational number. So we see that when we perform all these operations between two rational numbers, the output is always rational. Right? Now what happens when we perform these operations with irrational numbers? Let's say addition. Now in case of addition, let's say root over 3 plus root over 2. If we add them, what do we get? We get irrational number, right? But if we add root over 3 plus minus root over 3, if we add these two, what do we get? We get 0. And 0 is a rational number, correct? So in this case, it is a rational number. That means for addition, sometimes it may be rational, sometimes it may be irrational. Let's talk about subtraction. So in subtraction, root 2 minus root 2 will give 0, which is a rational number. But root 2 minus root 1 is an irrational number. Let's move on to multiplication. Root 2 multiplied by root 2 will give 2, which is a rational number. But root 2 multiplied by, let's say, root 3 will give root 6, which is an irrational number. Similarly, if we talk about division, root 2 by root 2 will give 1, which is a rational number. But root 2 by root 3 is an irrational number. Right? So in these cases, whenever we are doing these operations between two irrational numbers, we notice that the output may be rational or irrational. So both the possibilities are there. Now let us look at the third case where you have one rational number and another irrational number. And if you do addition, let us suppose 2 plus root 3. What is this? This is irrational number, right? So you take any rational and any irrational, the sum will always be irrational. If we do subtraction like 2 minus root 3, this will be irrational. We do multiplication as in 2 into root 3, irrational. We do division, root 2 by 3, irrational. So whenever we have one rational and one irrational number, then the output is always irrational. So this was interesting, isn't it? So we could clearly see with examples that when we perform these operations with two rational numbers, output is always rational. We perform with two irrational numbers, the output may be rational or may be irrational. If we do it with one rational and one irrational number, the output is always irrational. So now we are going to look at some questions, and the more we solve questions, the better our concepts will be. Check whether 7 root 5, 7 by root 5, root 2 plus 21, pi minus 2 are irrational numbers or not. Okay, let's take a look. So let's look at this number 7 root 5, one rational, one irrational, and their product. One rational, one irrational, that means the output will be irrational. 7 by root 5, again one rational, one irrational, so the output will be irrational. Root 2 plus 21, again one irrational plus a rational, so the output will be irrational. Pi minus 2, so pi is irrational, 2 is rational, so subtracting one irrational and one rational number, so the output will be irrational. So all of these are irrational numbers. Add 2 root 2 plus 5 root 3 and root 2 minus 3 root 3. So how do we do? So both of these are irrational numbers. So this is how we add them. 2 root 2 plus 5 root 3. So wherever we have similar root over, we will put them together. For example, root 2 under root 2, 3 root 3 under root 3, right? So what will be the value? 2 root 2 minus, so 2 root 2 plus 1 root 2. So this is basically 1 root 2. So this will be 3 root 2. 5 root 3 minus 3 root 3. So root 3 will be there. 5 minus 3 is 2. So not minus, yeah. So 5 minus 3 is 2. So this will be the sum. Multiply 6 root 5 by 2 root 5. So we will multiply the rational number. So 6 into 2 is 12. Root 5 into root 5 is 5. So this will be equal to 60. Divide 8 root 15 divided by 2 root 3. So we will deal the rational numbers together, like 8 divided by 2 is 4. And root over 15 by root over 3 is actually root over 15 by 3. So 3 5s are 15. So this will be equal to 4 root over 5. So this is how we handle the operations with rational and irrational numbers. Simplify the following expressions. So these are very simple simplifications rather. So we will make use of the properties like the commutative property, the associative and the distributive property, and we will solve them. So let's try the first one. 5 plus root 7 into 2 plus root 5. So what we will do? 5 multiplied by 2 plus 5 multiplied by root 5 plus root 7 multiplied by 2 plus root 7 multiplied by root 5. So let's do it. 5 into 2 plus 5 into root 5 plus 2 into root 7 plus root 7 into root 5. So this will be equal to 10 plus 5 root 5 plus 2 root 7 plus root over 35. So this would be the answer. Let's look at the second one. 5 plus root 5 into 5 minus root 5. So this is in the form of a plus b into a minus b. And what is a plus b into a minus b? That is equal to a square minus b square. Right? So a square minus b square. So 5 square is 25. Root 5 square is 5. So this will be equal to 20. Let's look at the third one. Root 3 plus root 7 whole square. This is of the form of a plus b whole square. And what is a plus b whole square? A square plus 2ab plus b square. So root 3 square is 3. 2 into root 3 into root 7, that is 21, plus root 7 square is 7. So this will be 2 root 21 plus 10. So that's the answer. Fourth one, root 11 minus root 7 into root 11 plus root 7. So this is in the form of a minus b into a plus b, which is again equal to a square minus b square. That is equal to root 11 square minus root 7 square. So that is 11 minus 7, which is equal to 4. Rationalize the denominator of 1 by root over 2. What do we mean by rationalize? So basically, if you see here, the denominator is an irrational number. Root 2 is irrational. So we have to rationalize it. That means the denominator should be a rational number. So how do we do that? So whenever it is a root over, so we multiply it with the same root, because we know that so for square roots, let's say it is root 2. Root 2, if you multiply by root 2, you get 2. Root 5, if you multiply it by root 5, you get 5, right? So therefore, what we do in such cases is we multiply it with the same square root. So we will multiply the numerator and denominator by root 2. So we get root 2 divided by 2. So the denominator is rationalized. Again, rationalize the denominator. In this case, it is root 3 minus root 5. So how can we rationalize it? So in this case, since it is in the form of a minus b, let us multiply it with a plus b, so that it becomes a square minus b square. Because in any case, we want to make it a square, so that it becomes a rational number. So we will multiply this entire thing by root 3 plus 5. Again, root 3 plus 5. So what happens? The numerator becomes 5 into root 3 plus root 5. And the denominator becomes a minus b into a plus b. So a square minus b square. So this becomes 5 into root 3 plus root 5 divided by 3 minus 5. So this is equal to minus 5 by 2 into root 3 plus root 5. So you see the denominator has been rationalized. So you are getting it, right? So whenever there is a square root in the denominator, if it is a single square root, just multiply it with the same square root. If it is in this form, then think of formulae which can convert it into a square, as in here. Right, because if you multiply it by root 3 minus 5 only, in that case what happens, it becomes a minus b whole square. So you get a square plus b square minus 2ab, and that 2ab will still be irrational. Therefore that a plus b whole square or a minus b whole square doesn't work. You need to make it a square minus b square. Classify the following numbers as rational or irrational. Let's try. 2 minus root 5. One rational number, one irrational number, they are getting subtracted. So the result would be irrational. So this is irrational. 3 plus root 23 minus root 23. So if we simplify it, these two will get cancelled. So the answer would be 3. So this is a rational number. 2 root 7 by 7 root 7. So root 7 will get cancelled. So this will eventually be 2 by 7, which is a rational number. 1 by root 2. So this is an irrational number. So even if we rationalize it, but we will still have an irrational number on the numerator. 2 pi. So pi is an irrational number. So obviously 2 pi will also be an irrational number. Simplify each of the following expressions. So see, in this particular part of the lesson, it's more about practicing these kind of expressions. How do you simplify them? That's the whole thing. So 3 plus root 3 into 2 plus root 2. Again, we will make use of the distributive property. So you multiply 3 with 2 and then with root 2. So you get 3 into 2 plus 3 into root 2 plus root 3 into 2 plus root 3 into root 2. So you get 6 plus 3 root 2 plus 2 root 3 plus root 6. That's the answer. Then you have 3 plus root 3 into 3 minus root 3, which is in the form of a plus b into a minus b, which is equal to a square minus b square. So this will be a square minus b square. So that is 9 minus 3, which is equal to 6. Then you have root 5 plus root 2 whole square, which is in the form of a plus b whole square. And a plus b whole square is a square plus b square plus 2ab. That is equal to 5 plus 2 plus 2 root 10. That is 7 plus 2 root 10. The last one, root 5 minus root 2 into root 5 plus root 2. So it is in the form of a minus b into a plus b, which is equal to a square minus b square. So I leave it for you as an exercise. So give it a try. So put it in the form of a square minus b square, that is root 5 square minus root 2 square. So now we are going to talk about the laws of exponents for real numbers. So whenever we have a base to the power something, right? For example, 2 to the power 3 is equal to 8. 2 to the power 3 means 2 is getting multiplied 3 times. So similarly, there are few laws that we need to remember. For example, a to the power m into a to the power n. What if you have the same base? So here a is called the base and m and n, they are called the powers or exponents. So in such cases, a is equal to a to the power m into a to the power n becomes equal to a to the power m plus n. So whenever they are getting multiplied, the powers get added up. Whenever they get divided, the powers get subtracted. So that we will see in the third one. So you see, when they get divided, the powers get subtracted. So a simple way to remember, a to the power m to the power n, that is equal to a to the power mn. That means, let's say 2 to the power 3 to the power 2. That actually means 2 to the power 3 into 2. That is 2 to the power 6. Right? If you have 2 to the power 2 into 2 to the power 3, that is actually 2 to the power 2 plus 3. That is 2 to the power 5. If you have 2 to the power 3 divided by 2 to the power 2, that is equal to 2 to the power 3 minus 2, which is equal to 2 to the power 1. And finally, a to the power m into b to the power m. For example, if you have 2 to the power 2 multiplied by 3 to the power 2, that actually means that 2 into 3 to the power 2, which is equal to 6 to the power 2. So these are the 4 laws which you need to remember. And based on these laws, let us practice a few questions. 2 to the power 2 by 3 into 2 to the power 1 by 3. So we see that the bases are the same and they are getting multiplied. So what will happen to the powers? The powers will get added up. So this becomes 2 to the power 3 by 3, which is equal to 2 to the power 1, that is 2. Let's look at the second one. 3 to the power 1 by 5 to the power 4. So this will get multiplied. So this becomes 3 to the power 4 by 5. Third one, division, same base. So the powers will get subtracted. 1 by 5 minus 1 by 3. So 1 by 5 minus 1 by 3 is equal to minus 2 by 15. This is like the normal subtraction. So that becomes the answer. Okay. Fourth one, 13 to the power 1 by 5 into 17 to the power 1 by 5. So 13 into 17 to the power 1 by 5, which is equal to 221 to the power 1 by 5. Let's practice few more questions. 9 to the power 3 by 2. So we have to simplify it further. So how can we simplify? Well, 9 being a perfect square can be written as 3 to the power 2 because 3 into 3 is 9. So 3 to the power 2 multiplied by 3 by 2 because 3 by 2 was already there. This 2 will get cancelled. So this becomes 3 to the power 3. 32 to the power 2 by 5. So 32, how do we write 32? So just do its LCM. 2 16s are 32, 2 8s are 16, 2 4s are 8, 2 2s are 4. So 32 is actually 2 to the power 5. So 2 to the power 5 multiplied by 2 by 5. So 5 will get cancelled. This is 2 to the power 2. So 3 to the power 3 is what? 27. 2 to the power 2 is what? 4. 16 to the power 3 by 4. So 16 can be written as 2 8s are 16, 2 4s are 8, 2 2s are 4. So this is 2 to the power 4 multiplied by 3 by 4. So 4 will get cancelled. This is 2 to the power 3 and that is equal to 8. 125 to the power minus 1 by 3. So what is 125? 5 into 25, 5 into 5. So 5 to the power 3 multiplied by minus 1 by 3. So 3 will get cancelled. This is 5 to the power minus 1, which is equal to 1 by 5. I hope you found the video useful. If you liked our videos, please do let us know in the comment section. Also share the video with your friends so that more and more students can get benefited out of this video. So I will meet you all very soon with a new video on a new chapter. Till then, bye-bye. Take care.